first step to getting robotic manipulators into the air. Research conducted by Nabeel under the supervision of Dr. Bishaban and Dr. Aliar. Drones. Over the last few decades, drones like these have been used in a variety of different ways. From entertainment-based applications like light shows and photography, to more crucial applications as an inspection tool in industries like energy, firefighting, and construction, drones have become an asset to ensuring public safety and the smooth operation of the services we use every single day. But what if drones could do more than just inspect? What if they could actively interact with their environment? What if they could collect samples, move objects, and actually assist us in dangerous situations? This idea is known as an uncrewed aerial manipulator, and it seems like an easy task, doesn't it? All we need to do is put an arm on a drone, and robotic arms have been around long enough that there should be a feasible way of doing it, right? Well, it's actually not as easy as it sounds, and the research around the idea has been quite limited. To understand exactly why, though, we need to look into how a robotic arm actually works in the first place. Robotic arms need to be extremely accurate in understanding their position so that they can be sure that they're in the right place to grab something, like that red ball. As such, they use a type of internal sensor called an encoder, and a smart placement of multiple of these encoders within the arm helps to identify the position that it's in. These encoders are only capable of capturing rotation in one direction, and as such have worked for many applications which require the arm to be fixed in place. However, they don't work for a drone, because the drone causes external movements and vibrations that these encoders are incapable of sensing, making it much harder to make contact with the object of interest. In essence, this all boils down to one research question. How can we address the lack of information about the position and orientation of a robotic manipulator that is attached to a moving base, all while making the research accessible and cost-effective enough for it to be employed in later research related to uncrewed aerial manipulators and beyond? That's exactly where my research comes into play. Over the course of 4 months, I was able to assist in the creation of a method to install, calibrate, and use an external sensor called an inertial measurement unit, or IMU for short, with any type of robotic arm to understand its position and orientation while it's on the move. Firstly, I designed a set of 3D printed mounts to mount the IMUs to the arm. Then, I iteratively tested a sequence of moves which gave enough information to calibrate the IMUs extrinsically, which means we find the location of the IMU with respect to the encoders, and intrinsically, where we find the internal parameters of each IMU. Lastly, I was able to help validate that the IMUs were displaying the correct position by comparing their data with the encoders over a set of many tries, which helped validate that the IMUs were correct. Amongst other interesting results, one of the most profound things that came out of this research was that the IMUs were actually able to capture both low and high frequency vibrations and contributed to a better understanding of the position and orientation of the arm at a much higher resolution than the encoders could capture. In fact, this research actually contributed to 2 conference papers and 1 journal paper as well. This research has the potential to be invaluable in the field, as it allows for a cheap, easy to set up, and accurate method of understanding the true position and orientation of a robotic manipulator while it's in the air. And further testing using high-definition motion capture cameras will be used to understand the accuracy of the method. Moreover, this research is not just limited to drones. This framework can be applied to anything that uses a robotic manipulator, such as garbage trucks, firefighting, and aerospace missions, or even medical surgeries, to decrease the reliance on expensive encoders and to increase the accuracy and repairability of these machines. As we progress into new territories of technology, exploration, and advancement, it is important for us to remember that even the smallest, cheapest devices can enable life-saving discoveries. Perhaps one day, even a high five